thanks so much for the introduction and for the invitation. It's a pleasure to be here. Yeah, so I'll be talking today about recent joint work with Daniel, Shachar, and Gaurav on realizable learning is all you need. So I want to, I don't want to assume any knowledge in this talk, so I want to start with a fairly, what's hopefully a fairly leisurely stroll through the theory of learning and Pac learning before we get into the results on this paper. So first of all, just at a very high level, when I say learning, what do I mean? Well, approximately, I mean something as follows. Let's let X be a set. Usually this is something called the instance space. And think about this as like R to the D or something like that, Euclidean space. And we'll let H be a family of binary classifiers on X. So this is just like 0, 1 labelings of the points in X. So maybe linear classifiers, half spaces. So here's an example where X is say R2, so two-dimensional plane. And your classifiers are maybe half spaces, linear or affine classifiers, and everything above the line is labeled 1. Everything below the line is labeled 0. This is just one example of a classifier in the class H. We'll be interested in studying what's called the learnability of pairs XH, which are called hypothesis classes. And what I mean by learnability here, in very brief, is that kind of given some hidden hypothesis H from the class, little h, given random samples of the form, random labeled samples of the form x, comma, the label of x with respect to h, is there some way that we can identify what h is? Maybe approximately or something like this. This is very broadly the overall idea. We'll get into some more details. So the model that I more or less want to focus on today or tell you about is something called the probably approximately correct model, the Pac model. And this was basically independently introduced by Vapnik and Chervonenkis to the statistics literature and later by Valiant to the CS literature. I think formally we probably take more of Valiant's approach here. Okay, so what is Pac learning? Well, I want you to think about Pac learning as a game between two players. A learner L and an adversary A. So how is this game played? Well, in the first turn, the adversary goes first, and the adversary is going to secretly pick kind of a hidden distribution D over the data and a hidden classifier from the family. So X and H are known to everybody in this game ahead of time, and A will secretly pick a distribution over X and a particular element, a particular classifier in the classifier family H. Now the learner will take his turn, and the learner will draw labeled samples from this distribution. So they'll draw points X from the instance space, and then they'll get the label with respect to the adversary secret classifier. So they'll draw a bunch of labeled samples, and then based on the samples that they receive, which we'll write as S throughout this talk, the learner L will try to output a guess for what H is. They're going to try to guess the adversary's hidden classifier. Now, what's the win condition? Well, the learner wins this game if their output, if their guess, which we'll denote as L of S, is close to H, is close to what the adversary chose. I'll formalize this in a second. And we'll say that L has a winning strategy, basically if they can win no matter what the adversary does. Like if for any choice of distribution and any choice of classifier in the family, we say L has a winning strategy if they win with high probability, no matter what the choice of the adversary is. Okay, so this is still a little bit informal. This is more formal than what I said in the first slide, but okay, what does it mean to be close to H? What does it mean to win with high probability? Let's formalize this a little bit before we move on. And to do this, before we play the game, we're actually going to fix fix two parameters, epsilon delta greater than 0. That'll help us formalize this. Epsilon is called the accuracy parameter, and this basically controls the definition of winning the game, of how close LS has to be to H to be considered kind of a win for the learner. So in particular, what we want is that we'll say the learner wins the game if their output LS has error less than or equal to epsilon. And what that means is that when you draw a point from the distribution, the probability that the learner misclassifies the point with respect to the adversary's classifier should be bounded by epsilon, should be less than or equal to epsilon. So that's the formal win condition. And what do we mean by winning strategy? Well, we mean that for all choices of distribution and hypothesis, the learner should win with probability at least 1 minus delta. So the learner's error should be less than or equal to epsilon, with probability greater than or equal to 1 minus delta. Okay, with this in mind, we can formally define what's called realizable Pac learning. So we say that a class XH is realizably Pac learnable with some sample complexity function n epsilon delta. This is some function like log 1 over delta over epsilon or something like this. If for all epsilon delta greater than 0, so for all choices of accuracy and confidence parameters, L has a winning strategy that uses at most n epsilon delta samples. So in other words, a class is Pac learnable basically when the learner has a winning strategy that uses a bounded number of samples. That's going to be our definition for Pac learnability. Okay, maybe I'll pause to ask if there are any questions about this definition, because it'll be kind of central to the rest of the talk. And I want to make sure people are on board.
Just checking, this is all specific to the 0-1 loss, right?
That is a good question. We'll talk about changing the loss a little bit later in the talk. For the moment, yes, for the moment, we're considering binary classification. In like half an hour, I'll maybe talk a little bit about extensions to non-binary cases, to stuff like regression, moving beyond the binary case. But for now, yes, we're just going to do binary classification.
Thanks.
Okay, then let's go ahead and move on to the next definition. So realizable learning is a little bit restrictive in the following sense. It forces the adversary to pick from this class H that is set ahead of time. Now, in terms of the game that I just told you about, this seems like a reasonable constraint. But if you actually want to go out, in practice and go out into the field and do applied ML, and you want to learn something, you want to learn some classifier on images or something, you're not guaranteed, like you don't know what the adversary is going to pick, right? It's not really realistic to take H to say be linear classifiers and just say, well, I'm going to assume my data is going to be linearly separable, right? It might just not be true. So in practice, this is kind of unrealistically restrictive for the adversary. So let's consider somewhat of a more realistic model that drops this assumption. So this is going to be something called the agnostic learning model. And in particular, in this version of the game, the agnostic game, the adversary will be allowed to pick any labeling at all. They're not restricted to picking a labeling from the class H. They can pick whatever they want. But the learner no longer needs to learn to within epsilon error. They only need to learn to kind of within epsilon of the best possible choice in H. So for instance, if H is like linear classifiers and the adversary picks some crazy function that's like 1/2 error away from every linear classifier, then the learner only has to pick something that's within 1/2 plus epsilon error. They don't have to get something within epsilon error because there's nothing in the class that's good enough. Okay, now let me formally say this a little bit more formally. That was just kind of an informal overview. So as I said, this model is called agnostic learning. And again, we're going to phrase it as a game between the learner and the adversary, the agnostic game. And it looks basically the same. So the idea is still going to be the adversary goes first, but instead of picking a distribution over X and a classifier from H, the adversary A will just pick an arbitrary joint distribution over X cross 0, 1. So samples from this joint distribution still look like labeled samples, right? They're pairs X, Y, where Y is a label 0 or 1 and X is something from the instance space X. But now it's a totally arbitrary distribution. It doesn't have to come from H. The rest of the game is basically played the same. So the learner will draw labeled samples from this joint distribution. And based on the samples that it receives, the learner will output kind of their best guess for this joint distribution in H. So they'll try to find like the closest possible thing, the best possible thing in H. And they'll win if their output LS is a good guess, kind of as good as possible or close to as good as possible. And we say they have a winning strategy if they win no matter what the adversary does, right? If they win with high probability for any choice of joint distribution. Okay, again, similarly to before, I'm going to formalize this with this epsilon and delta accuracy and confidence parameters. So what's the win condition? Well, the learner wins if their output is good, meaning that the error of their output, which is, again, this is just classification error. So this is the probability over the joint distribution that the learner misclassifies a point, right? That LS of X is not equal to the label Y. The probability of that is the error. And we want the error to be less than or equal to opt plus epsilon, where opt is the minimum error in the class. So if you're only learning things in the class, you can't hope to do better than opt, right? You can't hope to do better than the best possible thing in the class. So now we only want to get within opt plus epsilon. And note that if the adversary decides to choose something that is in fact a function in H, opt will be 0, and this will reduce to the realizable game. But they can choose whatever they want. So it's a little bit harder for the learner to win this game. And okay, a winning strategy is defined similarly to before. This just means that for all possible joint distributions, the learner is going to win with probability at least 1 minus delta, where again, winning means your error is less than or equal to opt plus epsilon. And then the formal definition for agnostic Pac learning is basically the same. We just want a winning strategy and a bounded number of samples. We don't want the learner to have to use infinite samples, basically, an unbounded number. So we say that XH is agnostically learnable with sample complexity m epsilon delta. If for all epsilon delta greater than 0, the learner has a winning strategy that uses at most m epsilon delta samples. Okay, so those are the basic definitions that we're going to be working with in this talk. And the first thing that you might notice, or at least, when I learned about these definitions, about this topic for the first time, it seems like agnostic learning should be way harder than realizable learning, right? In the agnostic model, like I mentioned, the adversary could choose something in the class, and that would just reduce back to realizable learning. So clearly, if you can agnostically learn, you can realizably learn. The adversary has kind of strictly more power. They can also just choose totally, bizarre functions that have nothing to do with the class. And the learner still has to figure out a way to kind of find the best possible thing in the class. And naively, it seems like this should be harder. But broadly speaking, it's not. It turns out it's a fairly classic result that these two models are information theoretically equivalent in the following sense: that a class, hypothesis class XH, is realizably learnable if and only if it is agnostically learnable. Now, I'm brushing some stuff under the rug. The number of samples that are required is different, but this learnability statement is the same. That one class, you're realizably learnable if and only if you are agnostically learnable. And how does the traditional proof of this go? Well, it relies on something called uniform convergence. And uniform convergence is the idea that if you draw a big enough labeled sample from the adversary's distribution, that the empirical error on that sample should give a good approximation for the true error of all the functions in H simultaneously. Now, this is for a single fixed hypothesis. This should be kind of obviously true, right? If you take a single hypothesis and you want to estimate its error, if you draw enough samples, this is just like the fact that the sample mean converges to the true mean, right? This is like a Chernoff bound or something like this. This is clear. But it's harder for this to be true simultaneously for all hypotheses in the class, right? Normally, you would have to union bound over all hypotheses to get this to be true, but H can be infinite, so you can't just union bound. So this uniform convergence statement really is a very strong statement. It's saying that on a large enough sample, not only is a fixed hypothesis being well estimated, all of this big infinite set of hypotheses is all at once simultaneously being well estimated. This is a very strong assumption. But it turns out that this is actually equivalent to learnability, to Pac learnability. It turns out that realizable learning, a class is realizably learnable if and only if it satisfies this uniform convergence property. And similarly, a class is agnostically learnable if and only if it satisfies this uniform convergence property. Maybe I'll mention, maybe you've heard about this as something called VC dimension before. VC dimension is also a parameter that is equivalent to uniform convergence, maybe a little bit more commonly talked about. But anyway, this is how you prove the result, right? You prove that both models are equivalent to some parameter or to satisfying uniform convergence, and therefore they're equivalent, right? They're both equal to the same thing, and so they must be equal. And that's true, but I don't know, to me, it's a little bit unsatisfying. It doesn't really tell you, like, if I can win the realizable game, why does this mean that I can win the agnostic game? It doesn't give an intuitive explanation of this. And furthermore, in the last 30 years, we've really wanted to move beyond the Pac model, right? The Pac model, sometimes it doesn't have guarantees that we want, right? Maybe we want to be robust, or we want to be private, or something like this. Or maybe it's too restrictive, right? Maybe we want to make distributional assumptions. Maybe we want to assume that the adversary is forced to pick some particular marginal distribution over the instance space. There's been a lot of different models that are kind of stem from the Pac model, but have moved beyond kind of the worst case guarantees or the exact definitions here. And uniform convergence no longer really works over these models. Like in distribution dependent learning, for instance, there are classes that are learnable in one sample, but don't have the uniform convergence property. In private learning, uniform convergence doesn't imply learnability. So this no longer works. You can no longer kind of characterize both things by uniform convergence and therefore claim, that they're equivalent. And this raises, to me, I think, a fairly natural question, which is whether the equivalence of realizable and agnostic learning is really a fundamental property of learnability, or whether it's just kind of a vestige of this original, Valiant's Pac model. When we move beyond the Pac model, when we move out of the kind of this uniform convergence paradigm, are we still going to have this equivalence? Are these models still really kind of more or less information theoretically equivalent? Or are things going to break down, like the equivalence with uniform convergence breaks down? Now, if you've been in the learning community for a while, if you're familiar with the literature, you probably have an inkling of what the answer to this is, because for pretty much every model studied in the past 30 years, close to the Pac model within learning theory, we've basically proved some form of equivalence of realizable and agnostic learnability, some variant. Maybe it's not exactly the same, but some version. This is true for when you fix the distribution. It's true for things like regression in some variants. It's true for a number of different versions of private learning, multi-class, robust, uniformly stable, partial, really just like almost anything. There's a little star here because it is possible to build kind of adversarial models with weird loss functions where it won't be true, but for most reasonable things, it seems to work. And the proofs are kind of mostly this similar kind of very roundabout thing where in the distribution dependent model, you prove that both realizable and agnostic learning are equivalent to certain type of covering, and therefore they're equivalent. All of these basically say you find something that both models are equivalent to, and therefore they're equivalent. There's kind of no direct explanation of why, and the proofs are all separate for the most part. All of these things have to be separately proved for each different model, and each of them uses different model specific assumptions. So it's not really clear what's going on here. And what I want to talk to you about today is whether there's some more general way to explain this phenomena. What's going on here? There's clearly something going on. We're changing the definition all over the place. We're looking at different versions of learnability, and yet somehow always realizable and agnostic learning are the same. What's going on? Until recently, we didn't know. And this is what I hope to convince you of today, that there is something more general going on. Okay, so maybe any questions about the setup before I move into trying to explain this? Okay, great. If not, I'll just go ahead and move on. So I claim that there is, in fact, a simple explanation for what is going on here. And what I'm going to show you is a two-step direct reduction from agnostic to realizable learning that does not rely on any model-specific parameters. It doesn't rely on uniform convergence or sample compression or Littlestone dimension or any kind of model-specific parameter. So here's approximately how it works. Let's say that L is a realizable learner for a class XH and uses some bounded number of samples. We're going to build an agnostic learner for the class. So we're going to turn a kind of a winning strategy for the realizable game into a winning strategy for the agnostic game in two steps. The first thing that we're going to do is build what I'm calling a cover of H. And I'll say that this is not a cover in the traditional sense. And on the next slide, I'll explain more about this. But basically, here's what you should think about this as meaning. We're going to take unlabeled samples from the adversary's distribution, and we're going to use our winning strategy to the realizable game to construct a small and crucially finite subset that approximates the class H well in some sense. So the big problem with learning things agnostically is when H is infinite. And so the first thing that we want to do is basically find a finite approximation for H. That's step one. And I'll explain everything in more detail in just a few minutes. Step two is that once we've kind of found this small finite approximation, so this, when I say a finite approximation, I mean a finite subset of hypotheses that does a good job somehow of looking like H. So now that I have this subset of hypotheses, instead of trying to learn H, I'm just going to learn the cover. I'm just going to learn the subset of hypotheses using kind of labeled samples from the adversary's distribution. I'm just going to try to find the best hypothesis in this finite subset that is supposed to approximate H in some sense. that I'll hope that because kind of this is the best hypothesis in my cover, and my cover approximates H, that it will be close to the best hypothesis in H. So this is kind of the overall, at a very high level, this is kind of the overall strategy. We build some finite approximation for H, and then we learn the finite approximation instead of learning H itself, which is harder because H is infinite. So that's the overall idea. Now I want to tell you what I mean by a cover, because we actually use kind of a new form of covering in this work. Something called non-uniform covering. It's basically a type of randomized cover. So let me define this for you. Let C be like a function or an algorithm that basically maps unlabeled samples that we'll write as SU to subsets of H, CSU. And CSU is basically this like resulting cover. So basically C is mapping samples to like potential covers of H, things that are supposed to kind of approximate H in some sense. And let's let dx denote the marginal of D over the instance space X. This is just the marginal of the adversary's distribution, just some notation. So we'll say that C, this algorithm mapping samples to subsets of H, we'll say that C is a non-uniform epsilon delta cover of H under this marginal distribution dx. If for every fixed hypothesis in H, if for every little h, the following statement is true with high probability over the sample, over unlabeled samples drawn from dx, so with probability 1 minus delta, there exists something in the cover, there exists something in CSU that is within epsilon distance of H. So with high probability, we want to make sure for every fixed H in H, we want to make sure with high probability that there exists something in the cover that is close to H. There exists some H prime that is within epsilon distance of H. And like I said before, we want our covers to be finite as well. So we'll call C bounded, basically if its support is finite, if these output sets, subsets CSU are all bounded in size. Okay, just to say this again in somewhat more intuitive language, because this is a long equation and it's hard to read these things and get them immediately in a talk. Really what we want is that for every fixed hypothesis in the class, that this kind of random variable CSU is going to cover H with high probability. It's going to have something close to H in the subset with high probability. That's really all that it is. And I want to make very explicit the fact that this guarantee does not mean that CSU is actually a cover for H, right? A subset is a cover, it's like a true cover for H if for every hypothesis in H, it has something close to it, right? So for every H in H, if you have, CSU should have something close to it, that's called a cover. This object is not a cover. It's not necessarily a cover. What your guarantee is that for every fixed hypothesis, when you run over the randomness, probably you're going to see something close to it. But that doesn't mean that everything is simultaneously covered, which would be something more like uniform convergence, right? And instead, we have a guarantee on each fixed hypothesis instead of having a guarantee on all hypotheses at once. And these are actually kind of provably different. You can quantitatively separate these objects. So I won't have time to go through that today. So, okay, the bottom line is that CSU, this set, is likely to miss some of the hypotheses each time. So it's not a uniform, what would be called a uniform cover. But this won't actually matter for us. Okay, I'm going to pause briefly and ask, are there questions on this definition? Because this is probably the most complicated thing we'll have to cover in the talk.
Hi, so if the cover, if the VC dimension is D, like how big is this cover?
Like the actual size of CSU?
Yeah.
It will end up being the size of SU to the D, something like that. If you have finite VC dimension. If you don't have finite VC dimension, it'll be exponential, like 2 to the SU, something like that. I'll say something about this a little bit more formally because I haven't told you how to construct this yet, right? I'm just defining the object. So I'll tell you how to actually build this, and we'll talk about what its size is when we actually build it.
Great, thanks.
Yeah, of course.
I have a question too.
Yeah,
so
sure.
The way you measure the difference between H and H prime, which is the error function you have there, it's the probability that you get a point from the marginal distribution on which H and H prime disagree, right?
Yes, correct. It is
Okay.
classification distance. Yeah,
Mhm. Okay,
exactly.
Good. Thanks.
Yeah, that's correct. Yeah, thanks. It's a good clarification. Okay, let's go ahead and move on. And actually, before I tell you how to build a non-uniform cover, I want to convince you that this is a useful object, that this is something you should be willing to pay attention to. And in particular, I want to go to step 2, which claims that kind of as soon as we have a non-uniform cover, agnostic learning actually becomes easy. And this will just follow from standard learning theory arguments, but I'm going to go through them because I don't want to assume anything for this talk. Okay, so why should you care about bounded non-uniform covers? Well, let me just repeat kind of what the guarantee is. We know for every fixed hypothesis in the class that over the randomness of our sample, CSU is going to contain some H prime close to H with high probability. That's the definition of a non-uniform cover. And notably, this is true for the optimal hypothesis in the class, right? Given the adversary's distribution, there's some optimal hypothesis H opt that achieves error opt, and it satisfies this guarantee. So what does that mean? That means formally that CSU probably, with high probability, contains some hypothesis H star that only disagrees with the optimum hypothesis H opt on an epsilon over 2 fraction of points. So say I have an epsilon over 2 non-uniform cover. I'm cheating a little bit here. So I have an epsilon over 2 non-uniform cover. And that means that the probability that H star is going to disagree with the optimal is at most epsilon over 2 with high probability. And furthermore, that means that the error of H star, well, it can't be more than epsilon over 2 worse than the error of H opt, which is opt by definition, right? Because it's equal to H opt for a 1 minus epsilon over 2 fraction of the time. And the rest of the time, the worst it can have is error 1. So the total worst error would be opt plus epsilon over 2. So H star isn't a perfect function. It's not exactly the optimum, but it's pretty close, right? It's like arbitrarily close. I can set epsilon to whatever I want. And in particular, I can get to within opt plus epsilon over 2, which is going to be enough. And so the idea now is that we're kind of guaranteed that this cover CSU is going to have a really good function, right? It's going to have something close to the optimal error. And so instead of trying to agnostically learn the full class H, now all I have to do is agnostically learn this kind of restricted finite class CSU, right? If I can learn the best hypothesis in CSU up to epsilon over 2 error, well, the best hypothesis in CSU has error at most opt plus epsilon over 2. So if I can learn this within epsilon over 2, what am I going to get? I'm going to get something within opt plus epsilon. And that was the definition of winning the game, right? That's how I win the agnostic game. I output something within opt plus epsilon. So all I have to do now, I've reduced the problem to learning this cover instead of learning the full hypothesis class H. And now, okay, if you've seen learning theory, you already know where I'm going with this. How do we learn this cover? How do we learn CSU agnostically? Well, CSU is finite. So this is actually pretty easy. You can use something called empirical risk minimization. The idea is that, and I mentioned this earlier, I think, when I was talking about uniform convergence, for any fixed hypothesis in the class, if you draw enough labeled samples, the empirical error of that hypothesis, like the probability that it messes up over these empirical samples, this approaches the true error, right? This is just like the sample mean converging to the mean. And this is by a Chernoff bound or something like this. And normally the problem is you'd want this to be true for everything in your class simultaneously. So you need uniform convergence, but H would be infinite. And so you can't union bound to get this. But CSU is now finite, right? So if I know that this is true with really high probability for every fixed hypothesis, and I have a finite set and I want it to be true for everything in my finite set, all I have to do is draw enough samples and union bound over the finite set, right? If I draw kind of sufficiently many samples and I know that everything in this finite set satisfies this guarantee with really high probability, with high enough probability, then union bounding over the size means that it will satisfy it for everything in CSU simultaneously. And once I have the fact that kind of the error of every function in CSU is well estimated by its empirical error, all I have to do is pick the function in CSU with the lowest empirical error. Right? If all of the functions, if I'm learning the true error, basically up to epsilon over 2 or something of every function in CSU, I'm guaranteed that if I pick the lowest one, I'm going to get something within opt plus epsilon. Why? Because it includes something, we know it has something that has error at most opt plus epsilon over 2. And so there will be something with good empirical error. And then by this fact that it's approaching the true error, I'm promised that kind of whatever I pick that has low empirical error is going to have good true error. So basically, I can just run empirical risk minimization, pick the best hypothesis on an empirical sample, And this will guarantee with high probability that I output something with an alpha plus epsilon error. And this is, the definition of winning the agnostic game. So once I have a non-uniform cover, I can win the agnostic game. Any questions on that before moving to the final step of the analysis? Okay, great. So this is fairly standard, right? Like if you've taken a learning theory class, this kind of learning of finite classes, this is one of the first things that you'll learn about. At least within
sorry, Max, can I ask a question?
Yeah, of course.
So in previous slide we had that CSU. Basically, so there exists an H prime in CSU for all but like a delta fraction of H in the capital H, right?
Not quite. That's it's a stronger guarantee than this. So that's, I think, true for every distribution over H, but the statement is a little bit different. It says for every fixed H with probability 1 minus delta over the samples, CSU will contain something close to H. That's a slightly different statement. It says like if you fix any hypothesis and you like draw an instance of the cover with probability 1 minus delta, it's going to cover that hypothesis.
And so why is this different from saying that CSU is a true cover for H?
It's not a true cover for H, because when you draw CSU, it's a true cover has to cover everything in H simultaneously, right? To be a true cover, it means that you are close to every hypothesis of H. But when I don't have that guarantee when I draw a cover from this distribution. All I have is that over. Okay, if your class is finite, it'll be the same, and if you draw enough samples, it'll be the same. Like if you have finite VC dimension or something, and then you repeat this process a bunch of times, you can get it to be a true cover. But from this formal definition, because H is infinite, getting from a 1 minus delta being covered to the entire thing being covered is non-trivial. It's not clear how to do this, and to do it actually requires provably more samples.
I see. Thank you.
But yeah, it's a good question. It's not obvious. It's a little bit of a subtle detail. Okay, so let's now move to I guess kind of the main thing. How do we actually build a bounded non-uniform cover? Right? I've showed you that if we have one, then we can agnostically learn. So how do we actually get one? And so we now finally arrive to the titular slide. And in particular, I claim that to build a bounded non-uniform cover, realizable learning is all you need. It turns out that you can do this by direct black box access to a realizable learner. So let's go ahead and see why. I want you to consider the following two-step algorithm for generating kind of a potential non-uniform cover C. So what do we do? Well, in the first step, we're going to draw an unlabeled sample from the marginal of the adversary's distribution, or just like draw a labeled sample and throw out the labels, ignore the labels. And it will be of size n epsilon over 2 delta over 2, where this is the sample complexity of the learner, of the realizable learner L that we're given, that we're using black box access to. And then, okay, given that I've drawn something dependent on the sample complexity, the next step maybe isn't that much of a surprise. I'm now going to run this realizable learner on all possible labelings of my unlabeled sample SU. So this set CSU, the kind of result of this non-uniform cover C, what I'm claiming is going to be a non-uniform cover on the unlabeled sample, is just the output of the learner on every possible labeling of the sample, right? For every H in the hypothesis class, we have the learner's output on SU and then the labels given by H of SU. Okay, so the first thing I'll note, and somebody was asking about this earlier, what's the size of this cover? Well, okay, by definition, I'm running over all possible labelings of SU, but labelings are binary, right? So how many labelings of SU are there? Well, certainly there are at most 2 to the SU, right? There are 2 options for each of SU things. So there are at most 2 to the SU labelings. So when I build this set, I'm by construction only adding in 2 to the SU things. So that's certainly bounded. There's a little asterisk here because if you have finite VC dimension, you can do better than this. You can get SU to the D instead of 2 to the SU. And this will get you better sample complexity, but it's not something that I want to focus on in this talk. So you can do slightly better, but for now, 2 to the SU is good enough for me. It's bounded. That's all I care about. Okay, the second claim is maybe the harder of the two. I claim that C is a non-uniform epsilon over 2, delta over 2 cover. And it seems like this might be hard, but in fact, I've fit the entire proof into the rest of this slide. It turns out that this is basically immediate from definition. You might have to stare at it a little bit, but it turns out it's pretty simple once you understand the definitions. So let me try to explain to you why this is true. Let me try to convince you. So first of all, what does realizable learning tell us? Well, the definition of realizable learning says that for any fixed hypothesis in the class, realizable learning promises that with high probability over samples, right, with probability 1 minus delta over 2, the output of the learner on a labeled sample, where the label is given by H, is within epsilon over 2 of H, with high probability. This is exactly the statement of winning the realizable game, right? The learner outputs something within epsilon over 2 of the adversary's choice, within epsilon over 2 of H, with probability 1 minus delta over 2. That is just the definition of realizable learning. And this is true for any fixed H in the class. Because remember, to kind of win the realizable game, the learner has to win for all choices of the adversary. So that for any fixed H, this statement is true, that the output is within epsilon over 2 with probability 1 minus delta over 2. But now I claim that we're done. Why? Well, by construction, this set CSU contains the output of the learner on every possible labeling. And that means if we look at any fixed H in the class, and we say, what's the probability that this cover is going to have something within epsilon over 2 of H? Well, it always contains this output of the learner. And we just said right above that the output of this learner is with probability 1 minus delta over 2 within epsilon over 2 of H. So for every fixed hypothesis, because we put all of these outputs of the learner into CSU by definition, for every hypothesis with probability 1 minus delta over 2, you're going to have something within epsilon over 2 of that hypothesis. So this set CSU, or this algorithm C for generating these sets CSU, is a bounded non-uniform epsilon over 2 delta over 2 cover. Okay, I'll pause for questions in this because this is the only proof I'm going to go through, and so the rest is we're going to talk about applications. But do people have questions on non-uniform covers, or how is this actually working? What's going on here before we move on?
So the size of CSU, you mentioned it's bounded by 2 to the SU, but I guess if, like Alex mentioned, if the VC dimension is finite, then we can bound it with Zauer's lemma. Is that right?
Yeah, you can use Darshal law parallels to bound this by SU to the D if you have VC dimension D. Yeah. So for instance, if you run this method using finite VC dimension, you basically get back the standard sample complexity bounds. So if you didn't do that, you would get like an extra factor of epsilon. But if you're careful and use Darshal law, you'll get kind of the classic, sample complexity back. So it is actually useful to use the better bound here.
Okay.
It's just not the main focus for the moment.
So we get back the like epsilon squared bound. I think it's epsilon squared.
Yeah. So you'll get from this naive analysis, you'll get log 1 over epsilon squared, which is like you can remove the log 1 over epsilon through chaining, I think. You have to be kind of careful. The naive solution will get you that.
Okay. Thanks.
Yeah. Okay. Any other questions before we move to talking about applications? Oh, actually, let me actually put together the whole algorithm so that we can see it all together. So hopefully this will help bring everything together, make it a little more cohesive. So let's review the full algorithm actually before we move on to applications. So recall that the first step is that the adversary picks some joint distribution d bar. We've been writing the marginal as dx, and we are given a kind of a winning strategy to the realizable game, right? We're giving a realizable learner L with some fixed sample complexity and epsilon delta, and we're trying to construct a winning strategy to the agnostic game. We're trying to build an agnostic learner. And we do this in these 2 steps. The first thing we do is we build a non-uniform cover. We just talked about this. So you do this by drawing an unlabeled sample SU and running script L over all possible labelings of SU under the class. And then we just learn the non-uniform cover, right? Now we run empirical risk minimization on the non-uniform cover. In particular, we draw a labeled sample And so here's the sample complexity we were just talking about, right? It's log the size of the cover over delta over epsilon squared. So now you see why the size of the cover matters in the conversation we were just talking about. This is the naive bound from Chernoff plus union. You can maybe do better, I'm not quite sure. And then you just return the hypothesis in CSU with the best empirical error. And we showed a couple slides ago that this is guaranteed to output something within oft plus epsilon with high probability. And that is exactly the definition of winning the agnostic game, right? So this is exactly an agnostic learner where we've taken the realizable strategy and we've kind of run it over unlabeled samples and we've gotten out a winning strategy for the agnostic game. And that is the full reduction, this two-step process. Okay, so maybe let me convince you that you should care about this reduction. Why should you care? Well, I think probably the most important point to make here is that the reduction doesn't use any model-specific properties at all, right? Namely, it does not rely on uniform convergence. Also, it doesn't rely on other things like sample compression or other techniques that are used to prove other versions of this equivalence in different models. And what this allows is that it makes it really easy to adapt beyond the Pac setting. So this allows, this reduction or slight variance of this reduction will work for all of the following settings: for distribution dependent learning, for regression or kind of more general, slightly more general loss, for robust learning, various versions of privacy, learning partial functions, even something like the statistical query model. You can get it to work for. So the fact that we don't rely on these model specific properties makes the reduction much more flexible. We can use it in a lot more scenarios. And I think, to me, we're not fully there, but this gives a much more intuitive explanation of why are realizable and agnostic learning equivalent? Why do we keep seeing this in so many models? I don't think the right explanation is, well, it turns out they're always characterized by the same thing. To me, giving a direct reduction between the two of them, right? Taking a strategy for the realizable game and turning it into a strategy for the agnostic game. To me, this is a much more satisfying answer for why these two models are equivalent than just saying, well, they're both equivalent to VC dimension or something like this. Okay, so these previous results that I have listed here were mostly known. You pretty much could just say like, okay, realizable and agnostic learning are both equivalent to sample compression, or they're both equivalent to Littlestone dimension or something. But let's talk about some new applications. Let's talk about some problems where you actually couldn't do this before. But now that we have this direct reduction, we actually are able to prove something. So my favorite instance of this, and probably the simplest, is learning with arbitrary distributional assumptions. In particular, if you talk to somebody who does machine learning in practice, and I think I've actually been told this explicitly by my peers in ML, Pac learning is often considered not super useful because it's extremely worst case. And when you try to like learn some natural imagery or something like this, there isn't an adversary picking like ridiculous finite layouts of points to trick you, right? It's like actually coming from some reasonable distribution or something like this. And one common way to kind of work with this type of relaxation in the literature, both in learning theory and in more applied side things, is to make distributional assumptions over the data, right? It's to assume that the data comes from a Gaussian with bounded variance or something with concentration and anti-concentration. And this is used a lot. And we can formalize this through this very general model, this generalization of Pac learning. And we'll look at the learnability of triples, script D x h, where script D is just some fixed family of distributions over X. And now the only change to the models is that the adversary is now going to be restricted. The adversary is going to be forced to pick a distribution from script D, say a Gaussian with bounded variance. And now this sounds great. Like this enables us to talk about learning with kind of any distributional assumption that you want. It turns out this is a really hard model to work with. It was worked on some in the 90s, but we still don't know how to characterize the model. We really know very little about it. It's very hard to work with because the fact that we don't have either kind of a finite set of distributions or all distributions make the combinatorial techniques that we're used to working with not work. Like uniform convergence fails immediately. We basically, as far as I know, don't really have techniques to work with this model. And I'll mention, like, it's possible that no combinatorial characterization of this model even exists. And And I say this because there's some related work on learnability being independent of some ZFC's set theory axioms. I don't want to get into this, but it's plausible that you can't even characterize learnability in this model, at least in standard set theory. Okay, suffice it to say, this is a hard model. That's the main point that I want to get across. We don't know how learning works in this model, but because our reduction is model independent and doesn't rely on properties like sample compression or uniform convergence, our reduction still works perfectly well with distributional assumptions, right? We still immediately get this corollary that a triple script dxh is realizably learnable if and only if it is agnostically learnable. And this is, on its own, I think this is a non-trivial statement about learnability in this model with arbitrary distributional assumptions, where before we couldn't say anything. We couldn't use these old proof techniques because we don't know how to characterize learnability in this model. And it's possible we never will, because it seems quite hard, or at least we're pretty far from it. And I'll note, this can also be combined with prior applications. So I'm cheating a little bit. I'm going to claim that we get like a huge amount of new applications just from this theorem, because we can go back to this list and I can say, well, what about robust learning where I make some distributional assumptions? Are realizable and agnostic learnability equivalent then? Well, yes, because you can just run our reduction. You couldn't do it before because we don't know how to characterize this, but now you have this two-step reduction, and with some modifications for robustness, it will still work. So you kind of immediately get everything to work with distributional assumptions, all of our previous knowledge, and you get kind of these nice extensions and a unified framework. So, okay, this is one application. The other one was something that was asked about that I wanted to talk about briefly, was asked about at the beginning of the talk, which is what about going beyond binary classification, right? So the setup that I told you about, this Pac setup, I was only using binary classification loss, but in practice, often many interesting problems we're not even doing classification, right? Maybe we're doing regression, we're doing linear regression or something like that. And now labels are maybe real numbers instead of 0, 1 classifiers, and the error isn't measured with respect to classification, it's measured with respect to LP loss or something like this. Or maybe you're trying to do robust learning, and so the error is measured with respect to robust loss instead of normal loss. I'm not going to go too much into these definitions, but I'll say that under kind of reasonable conditions, you can indeed get the reduction to work under these settings. In particular, we prove kind of tight variance of the equivalence of realizable and agnostic learnability in each of the following settings. If your label space is finite, so instead of being 0, 1, it's some finite set, you can get it to work for any loss function pretty easily. Slightly more generally, if you're over an infinite label space, but your loss is like nicely bounded in some way, you can get it to work. And then maybe the most realistically, we prove a version of the equivalence for loss functions that satisfy an approximate triangle inequality. So basically, you can think of this just as they kind of look like a distance measure. Like the loss function is kind of measuring some sort of distance between points, but it's not exactly a metric. Like it's allowed to have some slack. So for instance, like L2 loss would be a metric. It satisfies the triangle inequality, but square loss, where you don't take the square root, is not a metric. It's off. The triangle inequality is off by a factor of 2. But this is something that we can deal with this like approximate triangle inequality. So it's just something slightly more general. And I guess I'll mention the basic technique is, how am I going to deal with infinite label classes? Naively, there's a problem, right? If I run my reduction, how does it work? When I build a non-uniform cover, I run over all possible labelings. And if there are infinite possible labelings, I get an infinite object. I don't get a bounded non-uniform cover. And that's problematic for then learning the cover. So what you do is you basically discretize the class before you try to apply the reduction. So you try to discretize to some set that has with high probability bounded labels, and then you run the reduction. And this will work for reasonable scenarios, like if you have some kind of tail bound on your distribution or something like this. Anyway, I don't have time to get too much into it since I only have a few minutes left. Okay, so in the last maybe 5 minutes, I want to talk to you about going beyond agnostic learning. I want to claim to you that everything that we've talked about so far is really an instance of a more general phenomenon that's underlying learnability. And it's something we call property generalization. So basically, I'm going to let P denote what I call a learning property. And this is just like any property that you might want a learning algorithm to satisfy. So maybe you want the learning algorithm to be private, or maybe you want it to be robust to adversarial shifts, or you want it to be noise tolerant. Right? These are like properties of a learner. This is fairly informal. So agnostic learning is also a property. You want if the adversary chooses something weird and out of the class, you want the learner to still get kind of one of the best possible options. This is like a strong form of noise tolerance. It's some kind of learning property. And I'm going to call a property finitely satisfiable, basically if it works over finite classes. So if for every finite class xh, where I mean by finite, I mean that h is a finite set, we call P finitely satisfiable if there exists a learner with that property P for every finite class. And I'll note that, like we talked about earlier, agnostic learning is clearly finitely satisfiable because you can use empirical risk minimization, right? We talked about how once you have a finite class, if you just draw enough labeled samples and you take the best empirical error, you get an agnostic learner. So this is exactly what it means to be a finitely satisfiable property. Agnostic learning is a finitely satisfiable property. And so I claim that the equivalence of realizable and agnostic learnability is really actually just an instance of this more general phenomenon where you look at realizable versus any finitely satisfiable property of a learner. So here's kind of a general meta theorem. Take this with a grain of salt. It's more of a guiding principle than it really is a formal theorem. And it says that if P is any finitely satisfiable property, something that's kind of learnable over finite classes, and script L is a realizable learner for some possibly infinite class, xh, then I claim that basically by our reduction, L should be able to be used as a subroutine to build a learner for this infinite class that satisfies maybe some variant of property P, right? So if P is agnostic, this is what I've talked about for the last 45 minutes, that we can kind of boost L through this reduction to a learner satisfying the agnostic property. But I'm claiming now you can do this for anything that's finitely satisfiable. And why? Well, what we were doing in our reduction is once we reached the covering step, we basically applied the finite learner with property P, right? We applied the finite learner, the agnostic finite learner using ERM. So in this more variant of an arbitrary property P, instead of applying ERM in the reduction, instead of applying empirical risk minimization, I'm just going to apply whatever the finite learner I'm promised is for that property. Okay, now I know this is fairly high level and vague, so let me give you one application and then we'll end off the talk. This is the last thing to talk about. Let's talk briefly about privacy. So I'm only going to very informally talk about what this is, and I think some people in the audience might be a little bit more expert than I am on this, so feel free to jump in and correct me if I say something wrong. But an algorithm is private, more or less, if its output distribution doesn't change much on similar samples. When you maybe have a database, if you flip one label or you change kind of one person in a database, the algorithm is said to be private if the output distribution doesn't change much. And this is basically making sure that you can't reverse engineer who was in the data set and kind of what the labels were of people in the data set. And privacy is a classic example of a finitely satisfiable property. In particular, I'm not going to go through the theorem or proof, but it's been known for about 15 years now that any finite class can be privately learned by something called the exponential mechanism. And this is more or less, I'll go out kind of on a limb here and say that basically you can think about this for our purposes as adding some Gaussian noise and then still running some kind of empirical risk minimization process. But you add in noise to make sure that you're not kind of too dependent on any points. And I claim this will give you a private learner. Okay, I don't have time to go into anything more than that. So what happens if we try to run our reduction, but instead of using empirical risk minimization on CSU, we use the exponential mechanism? Well, we don't get a private learner out, and I claim that this is fine. In particular, this wouldn't be possible because private learning and realizable learning are not equivalent. Private learning is a much more restrictive condition. There are many classes that are realizably learnable that are not privately learnable. So we can't hope to get a private learner, but we do get something non-trivial. We get something called a semi-private learner. And basically what this is a model where you're mostly still private, but you have access to a little bit of public unlabeled data. So maybe you have some users who have kind of opted in and who have said, well, it's okay to reveal my participation in the study, but it's not okay to reveal, whether I was sick or not, or whether the medicine worked, or, don't reveal the results of the study, but, I'll opt in. It's okay to reveal that I was part of the study. So you think about it as kind of modeling this scenario where you have a little bit of kind of opt-in public unlabeled data that it's okay you don't have to be private with respect to this little bit of unlabeled data, but you still have to be private with respect to everything else. You can't leak any labels. You can't leak any of the private labeled data. And the goal in this model is to minimize the amount of public data that you use, because just generically, public data is harder to gather, right? It's easier to get data if you promise someone that it's going to stay private than if you just tell someone, okay, I'm going to release this public data. So you want to minimize the amount of public data. And I claim that from our reduction, you immediately get the following theorem, at least combined with kind of known work on sample complexity of realizable learning. I claim that if XH is a realizably learnable class, then it is possible, that is always possible to privately learn XH up to any epsilon accuracy using about 1/epsilon public unlabeled samples. So for instance, if I want to privately learn a threshold or something like this, that would normally be impossible to privately learn. If I have, if I want to learn this to 1% error and I have about 100 public samples, I can do this privately. Other than these 100 public samples that will get revealed, I can learn this, fully privately, which I think is nice. And I'll note that this result is tight. It turns out when a class XH can't be fully privately learned, when you can't learn the class with no unlabeled samples, public unlabeled samples, it turns out you need at least 1/epsilon. And this is a result from a couple of years ago of Alon, Vasily, and Moran. And of course, they also prove a similar upper bound. They're off by some factor, but it's pretty close. And basically, our reduction gives some improvement over this work by avoiding uniform convergence. The same thing we were talking about before. They managed to prove this result by using uniform convergence, basically building a uniform cover and making sure everything works at once. But there are a couple problems with this. First of all, getting uniform convergence requires more samples. So you don't hit exactly the optimal sample complexity by using uniform convergence. And second, this won't generalize to other models, right? Like, let's say that you want to do kind of this private learning problem, but you want to assume that you're coming from a Gaussian with bounded variance. You want to assume that you're coming from some nice distribution. Now this breaks down because you don't necessarily have uniform convergence, whereas this theorem will still hold, regardless of distributional assumptions or regardless of whether you want to learn partial functions or maybe you want to be robust. Like, all of these things will work because you don't care about model specific properties to use. We're just using this direct reduction that only relies on the definition of realizable learnability. Okay, that's the last application I wanted to talk about. I think I'm slightly over time. So maybe I'll skip this concluding slide and mention one or two open problems and then finish up if that's okay with the organizers.
Yeah, sure. Go ahead.
Okay, so let me just mention a couple open problems. So I listed a big number of models from the past 30 years or so that our reduction does kind of unify and handle. But I cheated a little bit. I left out a few that we can't really handle yet. And so let me talk about these a little bit. The first is private learning. And this is maybe a little bit confusing because I just talked about private learning and how our reduction works for a variant. But what I mean here is getting the reduction to work where you take a realizable private learner and you turn it into a realizable a realizable private learner and you turn it into an agnostic private learner. Our reduction does not work for this because when you build the cover, that process is not private. We don't know how to make that process private without kind of losing privacy from building the cover. We know that realizable and agnostic learning are equivalent in the private setting. You can use uniform convergence and various arguments to prove this. But it's open, for instance, whether this is true with distributional assumptions, because like all these other cases, you have to rely on uniform convergence and it won't generalize for this reason. So this is still an open problem. It's also known that infinite multi-class learning has this equivalence through connections with sample compression. This is also a problem for our reduction because you can't discretize the multi-class setting. And so you have this infinite label space. And when you try to run our cover, you get an infinite object, and it's not clear that you can agnostically learn the infinite object. So we kind of don't know how to deal with this type of scenario yet. This is open. And there are a huge number of learning models, and I'm sure that I've missed some ones that maybe people here study or are interested in. So, insert your favorite model. We cover a lot in the paper, but not everything. There are still a lot of models out there that either this equivalence is open or kind of a more direct reduction is open. The second thing I want to briefly mention is this study of non-uniform covers. So I introduced these new objects in this talk, and it's kind of our main tool for proving this reduction. It was kind of surprising to me that these hadn't been considered in the literature before. They're pretty closely connected with other forms of covering, like true covers we were trying to talk about earlier, or fractional covers. But I think that kind of they get at the theme of moving away from uniform convergence, right? Like in many previous notions of covering, you kind of needed to cover everything at once. But it turns out for scenarios in learning, we don't really need this, right? We just need like a fixed guarantee on one hypothesis. We don't need the guarantee on all hypotheses simultaneously. And I feel pretty strongly that this should be useful in other areas of learning theory beyond just this kind of agnostic to realizable connection, you know, maybe even in combinatorics, the study of set systems, or more broadly in computer science. And finally, I just wanted to mention and reiterate a little bit that actually the initial motivation for this project was studying learnability with arbitrary distributional assumptions and trying to kind of figure out what we could say about the model. Despite the fact that kind of all of the tools we knew about sample compression, uniform convergence, et cetera, fail. And we succeeded in saying something non-trivial, right? We got kind of these connections between agnostic and realizable learnability. We learned about these kind of non-uniform covers and their connection with learning with arbitrary distributions. And I think that this kind of gives us a new tool set for trying to study learnability with arbitrary distributional assumptions, or just more generally, models where this kind of uniform arguments didn't work so well before. We kind of, I hope that the tools that we introduce in this work maybe will lead to some progress in understanding on these harder models in the coming months or years. Okay, I'm over time, so apologies for that. Thanks for sticking around. That's everything I wanted to talk about.